start our discussion of discrete mathematics with counting, because counting will make up so much of part of the course, and we'll start counting with an example that will illustrate one of the main principles. The problem that we'll start with in this example is to count the number of two-letter words that are made up only of the letters B, C, D, and F. So we're looking at two-letter words using just B, C, D, and F. That's easy to count. You could list them quickly, but I want to show you a scheme that illustrates the general principle. So what we'll do is we'll take the letters that make up the words, the B, C, D, and F, and of course these aren't real words, but I'll use that in a very loose way. And what we're going to do is make a rectangular array where the B, C, D, and F in this column represent the first letter, and the B, C, D up here represent the second letter of the words that we're creating. And you can see pretty quickly then we get a rectangular array that includes all the letters, and there are 4 first letters and 4 second letters that are possible, and therefore there are 16, 4 times 4, two-letter words made from B, C, D, and F. So another way that sometimes people illustrate this product property that we have right here is to use a tree diagram where we just have a node here that just represents our starting for the branches, and we'll draw a branch here for B, the first letter that's available, and then another one for C, and then another one for D, and then another one for F. So we have 4 branches for the start, and then off of each of these branches we can use any one of B, C, D, and E for the second letter. So here we'd have B for the second letter, C, D, and F. And these 4 nodes here represent BB, BC, BD, BF. And so each of these would have 4 branches off of them. I'm not going to draw these all in with the letters, but each would have 4. And there are 16 nodes there for starting letters, for subsequent letters. That gives us a 4 times 4 equals 16 such words. So let's make this a little bit more complex by looking at a situation where we have the same words that we're thinking about, but now we're going to add a digit in the third spot to the right. So we're going to form all the two-letter words using B, C, D, and F, and then follow it by a digit, 1, 2, 3, 4, or 5, and see how many things we have in that case right there. And it's pretty easy to see how this is going on. Now we could imagine using a 3-dimensional array, but we don't need to do that because we've already counted how many two-letter words there are using B, C, D, and F. And so I've put those in this first column right here, all those words, and that represents the 16 words here with the 2 letters, and then up here we have the digits like so. And so with that, then we have 16 rows here and 5 columns, so we have a 16, 5, 5 array, and therefore we have 16 times 5 equals 80 such words, followed by a digit. Now that's equivalent to saying that we have 4 first letters, 4 second letters, and then 5 digits possible, or 80 total possibilities here. And I'll use this sort of a slot argument often in this case when we're talking about the product rule, which is what we're going to talk about next then. The product rule, which this illustrates, says that if we have a task, some sort of thing, for example, above we have the task of forming a 2-letter word followed by a digit. So that would be the whole task, to come up with something of the form like I have up here, DC3, the task is not completed until we have all three things in place. Suppose a task can be accomplished by using a sequence of k steps. Above we use 3 steps. So that the first step can be done in n1 ways, and then after you've done that, the second step can be done in n2 ways, independent of what the result was in the first way. And so on, so that after k minus 1 steps, the kth step can then be done in nk ways. Then the entire task can be completed in n1 times n2 through nk, that product, that number of ways. Now in the first couple of examples, everything was done because or in an order that corresponded to the way we would lay out the word from left to right. But things don't have to naturally come that way, but we'll try to organize them in a way where we can talk about step 1, step 2, etc. For example, this very simple example here, we have a fashion challenge freshman who has 3 pair of pants, 5 shirts, which are all t-shirts but different colors and patterns, and 1 pair of sandals. How many different ensembles are available for this freshman? Well, let's see. I'm going to do a slot argument. I'm going to try to describe at each stage what goes into the slots. So what I'm going to do is I'll choose to count the pants first, but we could have chosen to count the shirts first. That's what I mean by arranging it in steps according to what we think works best. So what I'm going to do here then is write down a slot here, and so this will be the number of pairs of pants, but I'll just say pants. And that's what? 3? Yeah. Times, for each pair of pants, there are 5 shirts available. This is the number of shirts. And then there's 1 pair of shoes. So the product of these tells us there are 15 different ensembles. There's an E missing here. Different ensembles. Okay? And so that's how we would conclude that example. And when you're doing this, I would like to see very much a display of this type here, where you're writing out the slots and you're describing what the different slots represent and the order of choices. So that's our first step, our first principle in counting.